This is the core component mock, and this is mock 1, and we're up to question 4, which is all about enzymes. So we are looking at fructose. It mentions the name of the enzyme there, isomerase. It's always good with enzyme questions to look for the substrate, the enzyme and the product. And we have got a substrate, glucose. It's flowing over the immobilized enzyme, which is isomerase, and then it's going to get turned into fructose. So we kind of know what's going on. And then we have the term immobilized enzymes, just a straight definition. So it's a enzyme trapped, held, supported, that sort of thing, in an inert matrix. Inert is not going to take any part in the reaction. Matrix just describes a structure for this enzyme to be suspended in. You could give an example of a type of gel or something, but we really want the term, the definition, and it's italicized there, immobilized. So that's the most the most important thing. Suggest 2 advantages. Well, there's plenty of advantages, and for example, if we're trapping the enzyme, then we can, certainly in this example, the fluid flows over the enzyme and the enzyme will carry on working but won't contaminate the product and can be reused. So the enzyme can be reused. It does not contaminate the product. So you're going to have fructose flowing out of this this situation, and the enzyme will not come out with it, so it's not contaminated. And we've got 2 there, but I'll put some more. And we don't need any more. The enzyme can withstand a greater range of pH or higher temperatures. It's not necessarily a range of temperatures that we can say there. A range of pH, because we will get denaturing either side of the pH optimum, but at lower temperatures, well, we don't get any denaturing, it's just a kinetic energy effect, so withstands higher temperatures. Then we have got a graph, and rate of flow on the bottom and the rate of product formation. So rate of substrate flowing against the rate of product formation. And you look at this graph and you go, this looks suspiciously like some of the other graphs that I know for enzymes. For example, an increase in the concentration of substrate against the rate of reaction. And that's essentially what it is, because we are increasing the concentration of the substrate by making it flow faster over the enzyme. So it's a similar sort of situation. When the rate of flow was increased from 2.5 to 4.5 dm³ per minute, that's litres per minute, or 1000 cm³ per minute. Calculate the increase in the product fructose production per hour and show you're working. It says show you're working. We've seen plenty of answers where they didn't get the final answer and the working was just a load of numbers, and so we couldn't credit any marks. We try and give you marks for stages of this calculation. So calculate the increase in fructose production per hour. So at 2.5. So there's 10 squares there, so 1, 2, 3, 4, 5, that's 2.5 there. And 4.5, 1, 2, 3, 4, 5. So what's the rate of production at 2.5? Well, we need to just fire a line up here and show your working. Well, this is your working for one of the marks, coming up with these numbers here from your graph. Okay, that's the 2.5, and the 4.5 is going up that line there. So most of the candidates who sat this managed to get these two lines on the graph sort of okay. So at 2.5 we've got a rate of 200 milligrams per minute, and at 4.5 we've got 300 milligrams per minute. So I'm going to write this out as well, just so we've got a full sort of answer. So at 2.5 dm cubed per minute, rate is 200 milligrams per minute. And do the same thing at 4.5 dm cubed per minute, rate is 300 milligrams per minute. And that's the first mark, clearly showing how you get in those two numbers. Then there's a calculation, so that we want a difference. So the difference between those two, so difference equals 300 minus 200 equals 100 milligrams per minute. And quite a few of you have given up there and gone, right, that's my answer. Well, we're not quite there yet. We're not quite there yet, because, lo and behold, there's a little trick. It says increase in fructose production per hour. Per hour. So at the end of the exam, when you get some spare time and you're looking through these questions trying to check them, and this is the sort of thing that you're going to spot second time around if you've missed it. So per hour. So if it's 100 per minute, well then there are 60 minutes in an hour, so we've got to equals 100 times by 60 equals in milligrams per hour. So 100 times by 60 is 6,000. You don't need your calculator for that. So 6,000 milligrams per hour, and that's our final answer. So how do we get 3 marks here? 3 marks for reading the graph and coming up with our 200 and 300. There's a mark for this number here, the 6,000. We're remembering to get the difference and times it by 60. And then there seems to be a mark for the units. So there's a couple of students managed to get the right answer and didn't put the units on and throw away a mark. And lastly, what is happening at flow rates above 6 dm cubed per minute? And this is explain. Well, we've got this kind of maximum rate, so I need to explain that, well, it's the maximum rate that we're going to get, sometimes called maximum turnover number or maximum rate of production. And the explanation is the same as your increase in concentration levelling off with the rate, and because the active sites are all in use, or they're saturated. So the rate levels off. I know it's a bit of a description there, but we've got plenty of space to say what we want. Rate levels off, reached a maximum rate of fructose production. And the actual explanation is that all enzyme active sites are in use, or we could say saturated. What we can't say is used up, because that implies that they won't be able to be used again. This is an enzyme, remember, so as soon as the product separates, then another substrate will be able to go in and bind to the active site. And so 8 marks. Main problems there were with this calculation and an explanation of this maximum rate.